see some examples. So the first example, so let us take V equals Rn with the norm 1. So remember, so norm x1 is sigma I equals 1 to n mod xi, where x is the vector x1, xn. So in short notation, Rn with norm 1, we will use the symbol ln1. Okay. W, any normed linear space. And T from ln1 to W, a linear map. Then T is continuous. So every linear map from ln1 into any normed linear space is automatically continuous. So how do we show this? So let us take EI to be the standard basis vector. So this is 1 in the ith place and 0 elsewhere. Then every x can be written as sigma I equals 1 to n xi ei. Therefore Tx by linearity is sigma I equals 1 to n xi tei. So now let us take k to be the max of norm tei in W, 1 less than equal to I less than equal to n. Now by the triangle inequality, you get that norm Tx in W is less than or equal to sigma I equals 1 to n mod xi norm tei in W, which is less than equal to k times sigma mod xi, which is nothing but norm x1. And therefore, by the definition of continuity, T is a continuous map. So this shows that every linear map from ln1 to any normed linear space is automatically continuous. Second example, let us take V equals little lp, 1 less than equal to p. So let me just take 1 less than p less than infinity. So x would be a sequence xi, okay, and you know that sigma mod xi power p is finite. So let p star be the conjugate exponent. That means 1 by p plus 1 by p star equal to 1. Then define f of x as equal to sigma I equals 1 to infinity xi yi, where y equals yi belongs to L p star. Then this is a linear functional. Okay, first of all, is it well defined? It is, because mod fx is less than or equal to sigma I equals 1 to infinity mod xi yi, which is less than or equal to, by Helder inequality, norm xp norm y p star. So this is Helder's inequality. Therefore, this is not only well defined, it tells you that this is a continuous linear functional. So this implies that f is a continuous linear functional, and norm of f is less than or equal to norm y in p star. One of the theorems which we will prove in this course is that every continuous linear functional on LP will occur in this way. This is the only way, these are the only functionals, and in fact you have equality here, norm f equal to norm yp star, and therefore you can say that the dual space V star of LP is nothing but LP star. That's why we have given the conjugate exponent that notation P star, because V star is in fact LP star. This is a theorem which we will ultimately prove. So this gives you an example of a continuous linear function. So now we have given an example in finite dimensions, an example in function sequence spaces. So now let us look at function spaces. So let us take C01 to be our base space V. Norm, remember, this is a sup norm. So norm F here is the max x in 01 mod f x. Okay, so now let K from 01 cross 01 to R continuous. So we take a continuous function in two variables. Then we define for f in V, f is a continuous function. I am going to define another function. So TF is also a function on 01. So TF on T is equal to integral 0 to S KST f of s ds. So this is called a Volterra integral operator. So we want to show two things. One is that TF belongs to V and T from V to V is continuous. It's linear, is clear. So we want to show these two things. Okay, so K is continuous on the compact set 01 cross 01. So it is uniformly continuous and bounded. So let us say we have that mod of K of ST is less than or equal to some constant K. Okay. Also, given any epsilon positive, it is uniformly continuous. Therefore, there exists a delta such that mod S1 minus S2 less than delta implies mod KS1 T minus KS2T is less than epsilon for all T. In fact, much more is true. I am using very little of the uniform continuity. You can also vary T within some similar delta, but I am going to take it only for a fixed T. So now we take TF at S1 minus TF at S2. Substitute, and then if you rearrange, so you can check this. This is 0 to S1, K of S1T minus K of S2T f of t dt okay, I think this is so this is S, and here sorry for that. Okay, ft dt plus integral S2 to S1 k of S2 dt f of t dt. So I've just added and subtracted things. So if you write out the two formulae, you will get this. So therefore mod Tf of S1 minus Tf of S2, if mod S1 minus S2 is less than delta, so this will be less than or equal to, from this is less than epsilon by what we just said, because S1 minus S2 is less than delta. We can pull out the Ft as norm f, the supremum can be taken out. So you just get S1 0 to S1 here. So you get epsilon times norm f into S1 plus k is less than or equal to delta, k is less than or equal to, is bounded. So this is less than or equal to k. S1 minus S, then again you have norm f, and then you have delta. So the whole thing is less than or equal to 1 plus k times norm f. So I am assuming that delta and epsilon are both less than 1, that's without loss of generality, and therefore this is times epsilon, and therefore this shows that Tf is a continuous function. And also you have that mod Tf of S is less than or equal to k times norm f times S, which is less than or equal to k times norm f, and if you take the maximum over S, you get that norm Tf is less than or equal to k times norm f. Therefore this tells you that this operator or mapping which we define T, so T from V to V is continuous and linear. Okay, so we have seen some examples of mappings which are continuous linear mappings. So let me give you finally an example of a mapping which is not continuous but linear. So let me take C1 0 1. So this is continuously differentiable maps, functions 0 1 to R. So we put the same norm after this is a subset or subspace of C01. And therefore we can put the same norm, this is a subspace. So now we define T from C1 0 1 to C01, both with the same sup norm, and T of f is f dash, the first derivative, because every function here is differentiable and the derivative is continuous, so this makes sense. So I want to show that this is not this is a linear map, but this is not continuous. So let us take fn of t equals t power n. Then what is tfn of t? So this is n times t to the n minus 1, because it's just the derivative. So norm of fn, which is the maximum of t power n in 0 1, this is 1. And what is the norm of t of fn? This is n. So we can never have an inequality like this. Because if we put f equals fn, the left hand side will be n less than or equal to k for all n. That is impossible because n tends to infinity, k is a fixed number. So this is an example of a mapping which is not continuous mapping, but which is nevertheless linear. Okay, so now we will look at some other properties like isomorphism of between norm linear spaces.